equations for exponential functions look like y equals a times b and then to the x power. So they still have a y, they still have an x, and now we introduce an a and a b. But that a and b are going to be kind of similar to things that we talked about with linear functions. So a is known as the y-intercept. So again, they're going to tell us where this crosses the y-axis, and that's good news. So we also know that the y-intercept in a real world situation is the initial value. Okay, so the a value is the y-intercept or the initial value. Again, this is provided to you in the module as a completed section of notes, so if I'm going too fast, remember you can always find those there. Now the b value is the multiplying factor. So it's how much we're multiplying by. And it's always going to be multiplication. Even when these things decrease, it's always going down. Now, we could also consider this a growth rate. So you're going to hear me say whether it's growing or decaying. So we call that a growth rate. So kind of double names for a lot of this stuff, which is unfortunate, but once we get the hang of it, not so bad. Now, I did say that these are going to grow or they're going to decay. They're going to increase or they're going to decrease. So when the b value is greater than 1, all right? When it's greater than 1, it is increasing. In other terms, it's going to be a growth. Because a lot of times we look at this with disease and different infections. And we all know about what's going on in our country right now. And then it's certainly a growth or an exponential model. Now the b value, when it's less than 1 or between 0 and 1, so let's write that. When the b value is between 0 and 1, oh boy, I'm running out of room here. When that b value is between 0 and 1, that's when it's doing the opposite. And that's when it's decreasing, or we call it decaying. So we have our growth and decay, we have our b values for that. Now another way to write this is that fancy compound inequality way where we put the smallest number on the left, then the less than symbol, then b, and then 1. And again, that's just another way to write between 0 and 1. Well, there's a little overview of the equation for an exponential model. Let's go ahead and look at it in terms of a graph. So here we have the equation y equals 2 times 3 to the x power. So we're going to be asked to graph this on the coordinate plane there, and we want to answer a few questions. So just by looking at the equation, we can come up with the initial value. That always sits right here. It's the a value. So the a value is really just 2. Now, is this growing or is this decaying? Well, look at the number in the parentheses, and if that number is greater than 1, it's growing or increasing. So this is a growth, meaning it's going to increase. And how much is it growing? Well, the b value is 3, which is greater than 1, and therefore going up. Now, to show a table of values for this, we're going to use our calculators. Remember that a table of values is just a list of x and y values. So I'm going to go ahead and pull up my calculator, and I got y equals already open, but just in case you don't know how to get there, remember it's the key at the top left, y equals. Clear out whatever it is that might already be there, and go ahead and enter it exactly as you see it, with the 2, with the parentheses, the 3, and then we need to raise it to the x power. So the only way you do that is with the little up arrow and then the variable key. So anything I just pressed is over here on the right side of the screen, so go ahead and use that. Now the table of values is going to be very important, or the window that is going to be very important. So with this exponential function, you can change this so we can see the growth. And a lot of times when it's growing, we need to increase the y maximum. So we need to make the y axis much larger. So let's maybe take it up to 100. Okay, so let's go ahead and press graph and see what's going on here. So you can see that if this is 100 up above, this really kind of increases and gets quite large. All right, now let's go to the table of values. Second graph, and here's where we want to write our list of values. It's kind of curious when we go up or when we go down, I guess the next value, that these numbers are decimals and they get to be very, very small, but you never see them actually be zero. Those are negative exponents showing showing how many times we've moved the decimal, but that is not a negative number. So we've got some really small values, but remember that it never actually gets to zero. And then we've got some other values that we're probably used to seeing, like 2, 6, 18, and 54. So let's go back to our table and write those down. Starting with 0, 0, and then 2. And nobody should be shocked by that because, again, that's our y-intercept. That's our very first point on the graph right there. And then we have 1, and that's going to be 6, and then 2 was 18, and the next one was going to be 54, 3 and 54. But that's all we can graph on this piece of graph paper. It's all the room we have. So if I'm going to graph this, I'm going to go 1 up 6, 1, 2, 3, 4, 5, 6, and then I got to find 18, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So right about there. So now we're just going to draw this, and instead of it being a straight line, it's got a little bit of a curve to it. Okay. Now we don't have anything over on this side, but I want to show you that we would never actually get below the x-axis because we would never actually go below 0. So they kind of make these what do we call these in the beginning of the year? They kind of make these banana shape patterns, right? Remember talking about the banana shapes, the horseshoes, and then the straight lines? So here's our exponential function in a banana shape. Now, where does all this come from? Remember this growth rate of 3? Well, look at this. We're doing times 3 and times 3. So a lot of this is found right in the equation or the graph. So let's see what we can get out of this. So we have the picture, and the important part is this right here. Again, the y-intercept of 0, 4. So the initial value, the y-intercept, we know it as the a value, is 4. Now the growth rate, how is this increasing? Look at the numbers in the y value, 8, 16, 32. The best way to find the growth rate is to divide the second y value by the first one. So pick any two y values and then divide them, as in terms of like 16 divided by 8, or maybe we want to do 8 divided by 4. As long as you take the y value and then the next one and divide them, you're going to find out that growth rate, which in this case all works out to be 2. So let's put this in exponential equation form, and that would be y equals initial value goes first, and then the growth rate or the multiplying factor, so it's multiplying by 2, and then the exponent is how many times we multiply by 2. Okay? So it's not that bad once we kind of get rolling with this, is it? Let's take a look at another one, but this time let's apply it to the real world and show you when you would ever use this. So here we have a situation where Michael Powers, has $10 in his bank account. If this amount doubles each month, then write an equation to represent the amount that he has after X number of months. We don't know really how long Michael wants to save for, but we know a few things. $10 in his bank account, and it's doubling. So this $10 is the A value, it's the initial value. So there's 10. That's what he started with. What is it multiplying by? What is its growth? This is the B value, the fact that it's doubling. So it's times 2. So let's put the equation down. We always start with y. It's equals. The initial value goes first. We're multiplying by 2 because we're doubling that, and we're going to do it for X months. So there you have it, the equation for Michael and his bank account. Now, if you ever wanted to figure out this in terms of the answer, let's say that this was 12 months. So, like 1 full year, how much would Michael have? All we would do is substitute that number in for X. So y equals 10 times 2 to the 12th power. And usually, very typically, the only way to solve these is with a calculator. So let me show you that. So let's say that we have our calculator out and open, and we want to do this. We would just leave out the y equals, and we would do 10 parenthesis 2, close your parenthesis, and then raise it up to the 12th power. So make it an exponent of 12. Once you do that, we'll find out that Michael has $40,960. Yes, these grow very, very quickly. So anticipate an exponential function growing very, very quickly, and that's why, and that's because we're multiplying instead of maybe adding like we would with a linear function. All right, we got a few minutes left, so I would like you, oops, sorry, this is still the same notes problem, but this one's a little different because the function is showing fractions. So just because it's showing fractions doesn't mean that's all bad. We're trying to figure out how this is increasing. And if you don't really know here with the fractions, that's okay. Look at numbers that you're more familiar with. How would you go from 1 to 3, from 3 to 9, from 9 to 27? And the key being multiplication. Yeah, it's times by 3. So always look to the table to see kind of how it's going, and look at the parts that kind of make more sense. Now our initial value can be found in a table wherever we see 0. So there's 0 and 1. So again, our A value, our starting value is 1. Our growth rate is times 3. We saw that how it's multiplying. Again, we could have used the idea of y2 divided by y1. So that would have been maybe 9 divided by 3. 27 divided by 9, something along those lines. Either way, you're going to get 3, but we put it together as an equation where the y-intercept goes first, the initial value, we're multiplying by 3, and then the x is now an exponent. All right? And I felt this was better to do the equations first and kind of see that because this is all about the graphs. So the graph of an exponential function, like we said, kind of can grow and go like this and look like this banana shape, or it can decay and decrease and look like this banana shape. But the key thing is these don't usually go below 0. They don't go below the x-axis. So therefore, the range is always greater than 0. So that's how you would show the range being greater than 0, and the domain, the x values, is always going in both directions. So we use all x values to the left and to the right. Now, in order to find the initial value, remember that that's the point right here where it crosses on the y-axis. We talked about it. So the initial value, the A value for this one, is simply 1. Now, the growth rate is how it's increasing. So from one point to the next. This was at 1. This was at 2. This is at 4. It's got to multiply to those numbers. If you're not sure, remember that the B value can be found by dividing two y values. If it's growing, make sure you always get a number that's bigger than 1. So in this case, 4 divided by 2 is simply 2. We could have looked at it as, 2 divided by 1. Asymptotes, don't worry about it. We're not going to talk about it in this class. That was put on the packet by the teacher that made it, but I'm not here to really talk about that. The domain is always the same. So there we go. All right, and the range is always the same. So you can just answer those by using that information there. That's not going to change. Let's go ahead and write the equation. So y equals, it's a 1 times 2, and we do it to the x power. So there you have it. All right, we got 1 minute left on the timer to get to 15, and that's all we're going to need because this one is a decaying or decreasing function, but it looks very similar in terms of its y-intercept. So there it is. It's crossing the y-axis at 1, so the A value is 1. The growth rate this time has some similar numbers like 4, 2, and 1, but this time we have to put the 4 in the bottom and the 2 in the top, because in order to find this y2 minus y1, the second y value would be 2. The first one would have been 4 because the 4 came before the 2, and so now it's 1/2. And because that number is between 0 and 1, then it's going to be a decrease. We're not worried about the asymptotes. Domain values use everything. So from negative infinity to positive infinity is the domain. The range values are all positive y values. So from 0 to positive infinity. That's not going to change for a lot of what we do, but the equation looks a little different each time, where it's y equals 1 times a half because it's decreasing, and we always do it to the x power. All right, so there you have it.